All right, and we are recording. So hello to everyone watching this. I'm Everett. I'm here with Kareem, and we're going to do a tutorial about sinuous antennas, and how to design one first in MATLAB and then in HFSS. And so, Kareem, you've been focused on sinuous antennas for a while, right?
That is correct, yes.
Yeah. So we're just going to go into how to design a four-arm sinuous antenna. And of course, we're going to start in MATLAB. Well, first, before we go into MATLAB, I want to show pretty much an article we're going off of. So this article right here is pretty much what we're going off of. And it gave us this nice equation. And this equation is what represents the sinuous antenna. So that's what we're going to use primarily. And now let's go into MATLAB. Right here. All right. So this is the spiral stuff from the other tutorials. Let's just make a new section here. And we'll just call this section sinuous antennas. All right. And then I'll just put some headers here. CLC, clear, close all. This is just good programming practice. All right, so looking back at that equation in the article, well, I'm looking back at it. So this is very interesting compared to the spirals, in that for spiral antennas, you put the angle into an equation and you get the radius, the magnitude. But for sinuous antennas, it's the opposite. You select how big you want your sinuous antenna to be, its magnitude, and then you plug it into the equation and you get the angles like that. So it's the opposite for sinuous antennas. So let's take a look at that article again. So looking at this article, we could see that our magnitude, our radius, has an initial radius, and then there's the final radius, which is r naught times tau to the n. And then we also have these other variables. We have alpha, we have tau, and we have delta. So looking in this article, we can see that delta determines the angular width of each arm. So from what I've been experimenting is maybe just around 20 to 60 degrees. Alpha is usually between 30 and 70 degrees, and then tau is usually between 1.2 and 1.5. So let's start by putting those variables into MATLAB. So we have tau here. And again, according to the article, tau is, I'm not sharing it. Yeah, here's MATLAB. So again, according to the article, tau is usually between 1.2 and 1.5. So let's just go in the center. Let's say 1.35. But tau is usually between 1.2 and 1.5. Then we have alpha here. And again, according to the article, alpha is usually between 30 and 70 degrees. So let's just use degrees to radians, because we'll most likely want it in radians, not degrees. And for now, let's just say, it said 30 and 70 degrees. So let's just say 50 degrees for now. But alpha is usually between 30 and 70 degrees. And then what other variables do we have? We also have delta and n. So delta, again, we'll use degrees to radians, is the angular width of each arm. So let's just say that's 60 degrees for now. And we'll see what happens. So delta is the angular width of the arm. We also have n here. So n is kind of like the number of turns for our spiral. It represents how big the sinuous antenna is in like number of turns. So n, let's just say, is 3 for now. And all right, it looks like we have almost all the variables. So let's start by defining our R, our independent variable R, which is, of course, the magnitude of the sinuous antenna. So we're going to specify an R naught. Let's just say R naught is 1 for now. So this is the initial radius. And then let's specify an R end, or how big the final value of our sinuous antenna, how truly big we want it to be. And let's just say R end is 5 for now. So this is the final radius. All right, so let's make our R vector. So let's say R is linspace. It starts at R naught, goes to R underscore end. And let's just say number of points is NP. Let's just say number of points is 1,000 for now. And okay, actually, wait, okay, I just remember that R end, if you remember from the article, R end is actually not a constant, or not like a chosen value. It's actually R naught times tau to the capital N. Again, so that's our final radius. All right, so now that we have our R vector here, let's just write the equation that's in the article. So according to the article, we have let's call this phi1. So phi1 equals, let's use positive delta right now, delta plus alpha sine. So we have alpha times sine of what? It's sine of pi natural log of R over R naught over natural log of tau. So we'll have a pi times natural log of R over R naught over natural log of tau. And that's what we call phi1, but we also need phi2, which is negative delta plus everything else here. So we'll have negative delta here. And if we run this, we have our phi vectors, we have our R vectors, everything is looking good. You following all right, Kareem?
Yes, so far so good.
All right, wonderful. Let me suppress these with a semicolon. All right, so now that we have our R vector and our phi1 and phi2, let's start plotting. Let's see what happens. So we'll plot again. Okay, again, we need to convert this into Cartesian coordinates. Right now we have polar coordinates, so we need to convert to Cartesian. And again, to convert to Cartesian, our x1 or our x variable is just going to be r times cosine of phi1. And then our y variable is r times sine of phi1. And then we also need for phi2, so we do r times cosine of phi2. And we do r times sine of phi2. All right, so let's plot those. So we plot x1, y1. Let's make this one blue. And then we'll hold on and we'll plot x2, y2, and we'll make that red. All right, so let's see what happens. Okay, and I forgot to use, this is element by element, so we have to do period times multiply. Let's run, and I still have to do it for these ones too. All right, so we're getting something right now. Actually, let's make both of these blue. So the thing is that our angular width, delta, it's 60 right now. That's really big. So let's just make that 20 right now. All right, and we can see it's all coming together. We have one arm of the sinuous antenna. So also let me change the axis limits just so we're not, so just so our plot is square. Let's just say that's 3 for now. And we'll do x lim, negative lim, positive lim, and y lim, negative lim, positive lim. Yeah, so we have one arm of our sinuous antenna. All right, so if we want to make our second arm, well, we just take all of these here. We just make these negatives. So we'll plot next negative x1, negative x2. Let's make this one red. And then we'll hold on. We'll plot negative x2, negative y2. Make this one red. Run this. And oh, this is supposed to be y2 here. Y1. There we go. All right, and we can see that our sinuous antenna is coming together very nicely. Does that make sense, Kareem?
Yes, this so far makes sense.
Yeah, everything's looking pretty good right now. So, let's observe in depth like what all these variables mean. So we can see that delta is the angular width of the arm, and what that means. So, for example, if we make this bigger, let's say from 20 to 40, we can see our spiral arms or our sinuous arms become more wider, right? Kareem, are you following?
Yes, I'm following.
Yeah, so they become much bigger. All right, so let's put that back to 20. And then if we change alpha, so alpha is at 50 right now, let's change it to 70 and see what happens. So if we change it to 70, we can see like the arms extend more towards they become more circular shape, like they're following the circle. And so that's what alpha does, is it alters how far these arms extend in the circular shape, if that makes sense. Let's change that back to 50 here. And then let's observe what tau does. So tau, let's make that 1.5. All right, so tau is kind of like the spiral factor from my spiral tutorials. It alters how fast these arms grow. So that's what tau is. Let's change it back to 1.35 here. And then n, of course, is like the number of turns, like in my spirals. So n, if we change it to 6, we'll see that we'll have will extend outwards more. So that's what n is. And let's change our limits here. Let's change that to, let's try 7. All right, so now let's think about our outer bounds and our inner bounds. So about our outer bounds, well, like in my spiral tutorials, if we want to make an outer bound, let's just make a piece of a circle that connects from here to here. And sinuous antennas are actually perfect for this because both edges here, the inner edge and outer edge, or well, both edges of the sinuous arms actually end at the same radius. We just need to figure out what those angles are. So let's put in let's call this phi1 underscore end. So phi1 underscore end equals this, but instead of the whole r vector, we're just going to plug in r underscore end. And phi2 underscore end equals all of this. But instead of the whole r vector, we're plugging in r underscore end. So if we found where the angles end, so let's make a vector with those. So we'll call this we'll just call this t for now. T is linspace phi1 underscore n, phi2 underscore n, and then let's just use np again. All right. And then we could just use the equation for a circle. Let's just call this let's just call this OB for outer bound. So it's going to be R underscore end times, or okay, so it's going to be X underscore OB, X for outer bound, is going to be R underscore N times cosine of T. And then Y underscore outer bound is going to be R underscore N times sine of T. All right, and then let's just plot those. So we'll do hold on, plot X underscore outer bound, Y underscore outer bound. Let's make this blue. If we plot that, we have our really nice outer bound here. And again, just to get the other side, we do the same thing, but we make these negative. And this is red here. All right, so we have our really nice outer bounds. And again, we can change all of these variables here. So for example, if we wanted to change capital N here to, let's say, 5, or let's say alpha to 45, or delta to, let's say, 25, and our outer bounds will still hold here. All right, but let's consider our inner bounds. Well, inner bounds are also pretty easy. Instead of a piece of a circle, we're just going to use a line to cover our inner bounds. So we need to figure out those angles. Well, again, we just need to plug in, instead of plugging in R underscore N, we're going to plug in R naught and see what phis we get. So we're going to get phi underscore start. Phi underscore start equals this right here. But instead of R underscore N, we're going to plug in R naught. And then phi 2 underscore start is delta plus or negative delta. Well, it's all this here, but instead of R underscore N, we're going to plug in R naught. And then, all right, so we have our phis. And again, we want to convert these to Cartesian, but again, we're going to use a line. So we don't exactly, we're not making a circle piece, we're making a line. So this is how we want to do this. So we'll call this we'll just call this X underscore inner bound for now. So that equals, sorry, let me think here. All right, so we want to do X underscore inner bound. So X underscore inner bound equals, well, it equals R naught times cosine of phi 1 underscore start. So this is phi 1. Then we'll do Y underscore inner bound equals R naught times sine of phi 1 underscore start. All right, but this is just the one of the coordinates here. So we need to make the other coordinates. So we have X underscore inner bound 2 equals R naught times sine of phi 2 underscore start. Then Y underscore inner bound equals R naught times sine of phi 2 underscore start. All right, so now we have our X and Y's. If we want to plot our inner bound, what we'll do, hold on, plot. All right, and this will be X underscore inner bound, or we'll actually make our vector here. So it'll be X underscore inner bound 1, comma, X underscore inner bound 2. Then we plot y underscore inner bound 1, comma, y underscore inner bound 2. And we'll make this blue. So if we do that, okay, that's not right. So what went wrong here? Oh, here it is. This is supposed to be cosine here. Now we have our very nice inner bound here. And again, to make the other side, we just make these negative. This is negative, and we'll make this red. All right, so we have our very nice inner bounds here. We have our outer bounds. So right now, we have two really nice sinuous antenna arms. Does this look good to you, Kareem?
This looks perfect.
Yeah, looking great so far. But again, most sinuous antennas don't have two arms. They have four arms, actually. So we want to get into how do we make those extra two arms. Well, we know that this delta here is an angle, and that changes like the angle of each of these edges here. Again, if we make delta, for example, something really big like 50, that makes the spiral arms very big. Well, let's use that. So let's turn this back to 25. So let's make a phi3. So phi3 will equal this, but we'll add in another variable we'll just call it angle 1. And angle 1, which we'll put up here, is just pi over 2. It's 90 degrees. And then we'll make our phi4, and this will be angle 1, but minus delta. All right, so we do that, and then we could just hold on. We can plot. And again, we need to change this to Cartesian coordinates. So we'll do x3 equals r times cosine of phi3. y3 equals r times sine of phi3. x4 equals r times cosine of phi4. y4 equals r times sine of phi4. So we plot these here, x3, y3. Let's make this one black. Then we'll hold on, plot x4, y4, and this is black. If we do that, and again, I forgot to use the element by element. So we'll put these periods here. And there we go. We have our third sinuous arm. And again, if we want to make our fourth one, we just take these and we make them negative. So this is negative x3, negative y3, negative x4, negative y4. And let's make these cyan or cyan. All right, and there's our fourth sinuous antenna arm. So again, we have to make outer bounds and inner bounds for these. So let's start with well, they're both going to be the same. We just make it negative when we plot. So right here, so phi3 underscore end is going to equal this, but we plug in r underscore end here. And phi4 underscore end is going to equal this, but we plug in r underscore n. All right, and then we just make a new, we make a independent variable. We'll just call this T2 to plot our outer bound. So T2 will equal linspace phi3 underscore end, phi4 underscore end. Let's just use NP. And then let's make our Cartesian coordinates. So this will be x underscore outer bound 2 will equal r underscore end times cosine of T2. Our y outer bound 2 will equal r underscore end times sine of T2. All right, so let's just plot that here. So we'll do hold on, plot x outer bound 2, y outer bound 2. We'll make this black. All right, so if we do that, we have a really nice outer bound. And again, to do it for the other one, we just take this and we make it negative. So x is negative, y is negative. We'll make this cyan or cyan. And there we go. We have our very nice outer bounds here. So we have all of our outer bounds. Now let's just finish making our inner bounds for these ones. So again, we go up here, we make our phi3 underscore start equals this stuff, but instead of r underscore n, we're going to plug in r naught. And then phi4 underscore start, again, equals this stuff, but we plug in r naught. And oh boy, what happened here? No, let's not do that. All right. All right, back on track here. All right, so we have our phi3 underscore start and our phi4 underscore start, and we want to make our Cartesian coordinates. So we'll do, this will be x underscore inner bound. We'll just call this x inner bound 3 for phi3. X underscore inner bound 3 is going to be r naught times cosine of phi3 underscore start. Y underscore inner bound 3 is going to be r naught times sine of phi3 underscore start. And then we have to make our other inner bound coordinates. So this will be x underscore inner bound 4 is r naught times cosine of phi4 underscore start. And then this will be y underscore inner bound 4 will equal r naught times sine phi4 underscore start. All right, then we'll just plot them here. Plotting x underscore inner bound 3. Oh, okay, we have to make it a vector here, so this will be x underscore inner bound 3. Y, or no, not y, but x underscore inner bound 4. Then we do y underscore inner bound 3, y underscore inner bound 4. This will be black here. And if we do this, we have the inner bound for the black arm. And again, we just make these negative here. So negative here, negative here, make this cyan. We have our inner bound here. All right. And now that is pretty much everything we need to know about the four-arm sinuous antenna in MATLAB. So this is a very robust design. We can change all of our variables here. So we can make tau, for example, maybe like 1.4. We can change alpha to something like 20 again, or 20 is too small. How about to 35? We can change delta to, let's say, 20. And number of turns, we can change to, let's say, 7. Run everything, and our design holds together. Let's change our limit here to 10 probably. All right, let's just make our n much smaller. Back to 5 here. And let's make tau a little smaller too. Let's just go 1.25. All right, a little too small. How about 1.3? Uh, 1.35 here. All right, let's just make our n much bigger then. Okay, that's all right. So that's everything we need to know in MATLAB. So Kareem, is that does that all seem good to you?
That all seems perfect.
Yeah. All right. So now that we have all of that, let's just move over to HFSS.